In other videos, we've looked at binary arithmetic, including division. And this is another video in the binary division line. But in this video, we're going to talk about doing binary division to calculate real valued results. So not integer quotients and integer remainders, but full-on real valued quotients that have a whole part and a fractional part. To do that, we're going to go back, as always, and start with something in decimal that we already understand. So let's divide 17 by 4. All right, they don't go, 4 doesn't divide 17 evenly, so we should get some fractional portion here, or some real portion. So 4 goes into 17 six times. 4 times, and that's going to give us a partial here of 16 that we'll subtract away and have 1 remaining. Now, if we were doing integer division, we would say that 17 divided by 4 is 4 with a remainder of 1. But in real division, we start extending the value we have here for the dividend in a way that doesn't change its actual value. Let me pick a color that's more visible. Red. By adding additional zeros beyond the radix point here. So now I can bring down more digits and give myself a partial dividend that I can continue dividing with. So now I'm doing 10 divided by 4, and that goes in twice and gives me 8, which I'll subtract from 10, and that'll leave me with 2. Since I don't have a remainder of 0, I continue to add zeros, bring them down. 20 divided by 4 is 5, and that'll give me 20, a remainder of 0. And now that I have a remainder of 0, I can stop dividing, because any further division or extension with zeros beyond the radix point is just going to give me more digits in the real part of the quotient that are zeros forever. So we just stop there. Now, in doing this, we have, inserted this radix point into our quotient to get a real valued answer. And so we would say that 17 divided by 4 is 4.25, or we might say 4 and 25 hundredths. And the reason we say 25 hundredths is because this digit, because of positional numbers, is the 10 to the 0th position, which is the ones position. This one here, where the 2 is, because it's to the right of 10 to the 0, has the exponent go down by 1, so it's 10 to the negative 1, which is equal to 1 over 10. That's the 2's position. The next position down is the 10 to the negative 2nd position, also known as the 100th position, or the 100th position. So, past the radix point, we can look at this sequence of digits as a full-on integer in isolation, in this case a 25. And so we would say we have a 25, 4 and 25, and then we give it its value based on the least significant position, which is the 100th position. 4 and 25 100ths. Now, if we were to have done a slightly different division, let's say 19 divided by 4, well, we can guess right away that since this is 1 shy of 20, this would have been a 4 with a remainder of 3, or you might even be able to do the mental math on this. That's 4.75. So using that same naming or speaking approach, we would read this as 4, and then we would read this part as 75 hundredths. So the way we do decimal division is important to revisit and to re-understand in terms of positional notations what each of these digits represent beyond the radix point. So we're into negative exponents. Now, we could do another division. So let's do, how about 14? I think this will fit the bill. 14 divided by 11. So 11 goes into 14 one time. We'll put 11 down here and subtract it away, and that'll leave us with 3. But our remainder is not 0. So if we want a real valued answer, we are going to have to insert our radix point and start expanding the value with zeros, which don't change it. Don't change its value or its magnitude away from 0. But give us the ability to have longer dividends to meet our divisor. And so 30 divided by 11, that's going to be 2. 2 times 11 is 22, so I'll subtract that from 30, and that'll leave me with 8. I still don't have a remainder of 0, so I'm going to bring down a new 0. Now I've got 80 divided by 11. That goes in 7 times. So I'll subtract 77 from 80. Then I'll get a 3. I don't have a remainder of 0, so I'll introduce a 0. Bring it down. And now I've got 30 divided by 11. But recall I already did 30 divided by 11. And at the point where I did 30 divided by 11, from this point forward, there'll be nothing in the dividend other than zeros. So while we could put the 2 here because we know 2 times 11 is 22, and that's what goes into this 30, we've also discovered that this value here is non-terminating and repeating. All right, more importantly, it's got a repeating portion here in the fractional element. So we have to also recall that some real quotients are non-terminating and or repeating. So we should see the same kinds of things when we consider doing this in binary. So let's look at doing some of this in binary. What about the original value we already did? What was it, 17 divided by 4? Let's say we want to do this in binary. So we need then 4, which is 1, 0, 0. And then we're going to divide that into 17. 17 will be 16, not 8, not 4, not 2, and 1. 16 and 1 is 17. So this is the division we're going to do. So here's 100, or 100, 100 into 100. That goes in once. And now we've got to deal with the difference. Remember, we're going to apply the 2's complement negation to this isolated 3-bit pattern. So we're going to end up with 0, 1, 1, plus 1 for flipping all the bits and adding 1, which oddly will give us a 0, carry the 1, 0, carry the 1, 1. The same bit pattern we started with. So we're going to add that bit pattern. And then we'll get 0, 0, and a 0, carry the 1, but we're only going to keep track of the bottom 3 digits here, so we're just going to throw out that carry to the bit bucket. Now we're going to bring down another 0, and we don't even have a 1 here, so this can't go into it. So we'll have a 0 here. We'll bring down the 1 here, and finally we at least have a digit. But 1 divided by 100 is not going to happen. This is 1 over 4, so we're going to end up again with an additional 0. And now we've reached the end of our integer division. We could say we have an integer quotient of 4 with an integer remainder of 1, but we want to find the real valued quotient. So we're going to go ahead and introduce the radix point and start adding some zeros. Now I know because I have a 1 here and that's it, I'm going to need at least 2 zeros to have 3 digits for my 3-digit divisor. So here they are, and that means we would have gotten a 0 here. And now we have 100 divided by 100. That goes in once. So we will add this to find our remainder. We'll get 0, we'll get 0, and then we'll get 0, carry the 1, but we're only going to keep the bottom 3 bits here because our divisor is 3 bits. And now we have a remainder of 0, so we can stop here, in which case we say that 17 divided by 4 is equal to 100.01 in binary. And in binary now, when we get over here, past the radix point, we're looking at the 2 to the negative first position, which is equal to 1/2. That's this guy. And then the 1 is in the 2 to the negative 2 power position, which is the same thing as 1 over 2 squared, or 1 over 4. So this is the 4ths position, which means, again, for reading this out, we're going to take this 2-digit number as a standalone integer, the number 1. And that means our remainder portion is 1 over the value of the least significant bit position, and that's 4. So what we have here is 100. This is effectively the number 4. And this part says that we have 1/4. Right? And that matches what we saw before, where we were looking at 25 100ths, because 1/4 is equal to 25 over 100. Right? It's just simplified. So similarly to what we did in decimal, if this is the case, we could imagine that if we bump this up to doing 19 over 4, we know in what we had done in decimal that we ought to get 4 and 75 100ths. And 75 100ths would simplify down to 3/4. So we ought to get 4 and 3/4. Right, so we can assume in binary then that we will get the answer 1 0 0, and then 3/4. Well, we're going to use bits up to the 4th position, so that's 2 bits, and we need the number 3 and 2 bits, so that's 3. Right. So this is 4 and 3/4. Now we just want to verify that that's actually what's going to happen, so let's do the division. Let's see here, that's 4 getting divided into 19, which will be 16, no 8s, no 4s, 16 plus 3, so we need 2 and 1. All right, so there's 19 divided by 4. Again, we do our negation, and we discover from up here that we end up with the same bit pattern. But that's okay. That's how we'll do it. So this goes in once, so we'll add 100. Or 100. We'll add 1 0 0. We get 0 0 0, carry the 1, but we throw the carry to the bit bucket and leave this alone. Now we'll have to bring down a 1, and 1 is not divisible by 1 0 0. We'll bring down another 1. 1 1 is not divisible by this because it's too few bits. We get another 0. And then it's time to introduce additional digits. So let's put a 0 here and bring it down. Now I have 1 1 0 divided by 1 0 0. So if we start scanning, match, because of the same size, we have a match here, and then no match. But because the partial dividend has a 1, that means this will be a 1. Now we'll add 1 0 0 to that, and we'll get 0 1 1. Nope, 0 1, and then this is 0, carry the 1. Ooh, that would have been a terrible blunder. Now we've got 1 0, which is 2 digits, and we mechanically always bring down the next digit, which will have to be a 0. Now we have 1 0 0 divided by 1 0 0. They're the same length, and they're the same value. So that means it goes in once. And now we'll add 1 0 0, our pattern here. And we'll get 0 0 0, carry the 1, but we're going to forget about that carry because it's beyond our 3 bits. And now we have a remainder of 0, and we can see we got the same result that we would have assumed we would get over here, which is 100.11. Now we can always then take, once we understand this, we don't have to necessarily even do the division. I could give you a number, for example, like, I don't know, 12 and 13/16, let's say. I could say 12 and 13/16. I wish I knew what that looked like in binary. And the first thing we could notice is that this value here is a power of 2, and it's on the bottom side. It's on the denominator of a fraction, right? So since this is a power of 2, this 16 is 2 to the 4th, we know that this will map to 2 to the negative 4th. And so we can jump right away from this to its binary equivalent. So let's write 12, which will be 8 plus 4, no 2's, no 1's, a radix point, and then we need the number 13 in the correct number of digits. Since 16 is 2 to the 4th, and the 1/16th position will be in 2 to the negative 4th, we know we have 4 bits to work with. So in 4 bits, I need to write the number 13. So that will be, let's see, 8 plus 4, no 2's because I've got 12 so far, plus 1 more is 13. And so now here's the halves, fourths, eighths, and 16ths bits. And this little bit here is 13. But it ends on the 16th position. Now, understanding how many bits are required for the bottom is critical here. So if I wanted to do a similar thing, and let's say I'm going to do 17 and 3 30-seconds. I'm choosing 30 seconds here because this is a power of 2 again. And this is 2 to the 5th. And since it's the 1 over 32 fraction, this is 2 to the negative 5th is 1/32. So that means we're going to need 5 bits beyond the radix point to represent the 3 30-seconds. So first let's do 17. That'll be 16 plus no 8's, no 4's, no 2's, and a 1. And then in 5 bits, because this is the going to use up to the 2 to the negative 5th position, I need to write the number 3. So 5 bits, the number 3. And 3 is really just 1, 1. So I need to do 3 zeros, and then my 2 1's, and I've used 5 bits. And so this is 3 30-seconds. Now it would have been absolutely wrong to do 1 0 0 0 1 and then write down the number 3 directly, 1 1. This is not the same thing as that. These do not equal one another at all. This is the same fractional portion that we saw up here. This is the number 17, and then here is 3 quarters. So this is 17 3/4. You must look, if you're going from this representation, a decimal fraction representation, to the binary representation, you must consider what the base of that is going to be. Okay. All right, so there's a couple good examples of binary real division. Now, when we did it in decimal, we also noted that some quotients are non-terminating and repeating, and we should see the same kind of phenomena in binary. So let's take a look at some of that. Let's do 19 divided by 3. All right, so that's the same thing as saying 1 0 0 1 1. This is 16 plus 3 is 19. Divided by 1 1 in binary is 3. So 1 1. We'll pull this over. Let's see here. 19 is 1 0 0 1 1. Now 1 1 doesn't go into 1 0. We've got 2 bits here, but the 1 1 is higher, so we would end up with a 0 here. So we've got to go to 1 0 0. Because that has more bits than this, it goes in once. Now we need to figure out what the negation of this is, so we're going to flip all the bits and add 1, and that'll give us the bit pattern 0 1. So in the bottom 2 bits here, I'll add 0 1, and I'll get 1 and 0. Bring down the next 1. Now I've got 1 1 divided by 1 1. That goes in perfectly. Now I'll add 0 1. That'll give me a 0, carry the 1. 0, carry the 1, but I only care about 2 bits because the divisor is 2 bits. Bring down a 1 here, and I've got 1 divided by 1 1, so this has got fewer bits, so I'm going to get a 0 for sure. And then I run out of bits in my dividend. So I just put in the radix point and start adding zeros. I bring the 0 down, I got 1, 0 divided by 1, 1. They're the same number of bits, so I'll scan through for differences. Same, different. The dividend has the 0, so the 0 goes up here. That means we need another digit. There we go. 3 bits divided by 2 bits. We get a 1 for sure. Add the 2-bit value 0, 1. Now I'll get 1 and 0 here. All right, now I'm going to bring down, because this is 1 bit divided by 2 bits, so that can't go. And let's see here, I'll bring down a 0. Now I've got 1, 0 divided by 1, 1. That doesn't go in. Here's the mismatch bit where this one is lower, so I got to do another 0, bring that one down. Now I've got 1, 0, 0, 3 bits divided by 2 bits. Hey, that's going to be a 1. And I could keep doing this all day. And we should have known that we could stop right around here, because here we had a remainder from one of our elements of work of just a single 1. And we've already seen, I think we saw that up here. Did we see it up here? Oh, we did see it right here, but it doesn't work the same way. So we wouldn't have known it then. We would have needed to get out to about here. So here we have a remainder of 1. Yeah, this is the spot. Let me mark this some kind of a color. So here we had a 1 that only can have zeros coming after it, right? So we're effectively seeing that 100 here, or 100 there, not 100, divided by 1, 1. And here we are seeing that exact same thing again. And as a side effect, we can tell that everything between this bit and this bit is going to repeat. So the 0, 1 is going to repeat forever. So we could remark this and say that 19 divided by 3 is really equal to 110.01 repeating in binary. So we have repeating and non-terminating values in binary real division, just like we do in decimal. But there is at least one other that I want to show you that's a super critical one for us when we are writing software. It's super important that we know about it. And that's 1 divided by 10, or 1/10. Now this is decimal, not binary. And that's the same thing as 1 binary divided by 10 in binary, which is 8 and 2 binary. So let's do this. I've got 1, 0, 1, 0, and I'm going to divide that into 1. Ta-da! Now 1, of course, is too small, so we know we're going to get some zeros very early on. But let's figure out what the negation of this is. First, I'll flip all the bits, then I'll add 1, and we'll get 0, 1, 1, 0. So this is the thing that we're going to add at each step of our division. Now we've already run out of useful digits, so we know this goes in 0 times. We'll introduce our radix point and start adding some zeros. Now we need at least 4 bits to even have a chance, so I'll write 3 zeros here. And that means these guys must have gone in no times as well. Now we'll scan. 1s are the same, 0's the same. Here's a bit that's different, because this is a 0. The partial quotient will get a 0. So we add an additional bit. Now we've got 5 bits divided by 4 bits, so it's definitely going to go. So I'm going to add, goes in once, and then we're going to add this to the bottom 4 bits. 0, 1, 1, 0. That'll give me a 0. 0 plus 1 is 1. 0 plus 1 is 1. 0 plus 0 is 0. All right, now I've got to bring in another digit since I don't have a 0 remainder. And I've got 1, 1, 0, 0. That's 4 bits divided by 4 bits. So let's scan them for differences. Same, different. So this dividend bit has a 1 in it. That's what's going to go up here. All right, now we're going to add to the bottom 4 bits. 0, 1, 1, 0. The value we found here. 0 plus 0, 0 plus 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. All right, now this is a 2-bit number, and to divide it by 4 bits, I'll need at least 2 more bits. And so we know this is a 0. For our 4-bit patterns, we compare them. 1, 1, 0, 0, 0, 1. Oops, this is different, and this is a 0, so we're going to put a 0 here, which means we need another digit. Now we got a 5-digit number, a 1 followed by 4 zeros, to be divided by this. And we know it will go in one time. However, if we look back at what we were doing before, we see that back in time, we had a 1 followed by 4 zeros that will only be followed by zeros after that, being divided by our divisor. And here we are with a 1 followed by the 4 zeros being divided as such forever. So we can tell, since this one had a 1, and here we are back with the 1 again, we're going to now get this another 1, and then a 0 and a 0, and then 2 more 1s and a 0 and a 0, and so on. And so really, this part of the pattern, 2 zeros and 2 1s, repeats indefinitely. And that means that we can say that 1 divided by 10 is going to give us 0.00011 with these last 4 bits repeating in binary. And the reason that is so important is because it tells us that we can't represent 1/10 accurately with binary real values. Now, why does that matter? Well, if for nothing else, your bank, when it tracks how much money you have or how much money you owe, does so in terms of dollars and cents, right? And if you take 1/10 of a dollar, you'll get a dime. And if you want to have a penny, you got to take 1/10 of a dime. So that's 1/10 of 1/10 to get 1/100th. But if you can't accurately represent 1/10, you're not going to be able to accurately represent 1/10 of 1/10, right? The error compounds. And so we can't use binary real values to accurately represent our finances because the values will be wrong. As such, it is critically important that we don't use these things to represent certain types of data where the base 10 that we understand these data in is going to cause a problem when we get into fractional elements. So when we write financial software, just as an example, we don't use binary real numbers. If we were to do that, it would be very foolish. Instead, we will use some kind of implementation of binary coded decimal, let's say, so that we can perform arithmetic on those numbers and keep the tenths and the hundredths accurate, and preferably even to greater precision than that. So that is binary real division. If you have any questions, please post comments below. The last division related video or topic that we need to consider is division that gives us real values in the form of floating point.